saved off?
You. No, I don't think so.
Oh, I thought you ran like 10 points.
Oh.
You still like to the right down the elevator?
Yeah. Is it? Did the class start?
Yeah, you started.
Did it say 5, 4, 3, 2, 1?
Yeah.
Okay, good. Because I boilercast this so that these, basically what you see here is what you're going to get in the aftermath. So this is Math 341, Foundations of Real Analysis, which in old days used to be called Advanced Calculus. And for me, taking it, I was an engineering undergrad at Michigan. Really wanted to be a math major, but back then people were telling me I couldn't get a job doing math, which turned out not to be true. Anyway, this is a subject which I was really dying to know, and convinced me that my path would be better if I studied the foundations of mathematics and sort of the more deeper things about math rather than applications. So for me, it was a really important class, and had a great teacher back at Michigan who really fired me up about the subject. I kept my notes. I still have them and look at them. The course, I'm going to get all the information you need about it on the web rather than on Brightspace. So when you go to Brightspace, you'll get links to go to the home page, and that's where all the information about the course will be, including lecture notes and videos of the lectures, etc. Let me show you what that web page looks like. There it is. Let's see, the book is this nice book, I think you'll like it, called Introduction to Real Analysis by Bartle and Sherbert. And it's going to be very important to read the book carefully and follow it carefully too. Because every now and then I'll tell you to read the book instead of me talking about it. Especially this very first section is stuff you've probably heard a million times, and I don't want to bore you to death with it. Okay, we'll probably cover most of chapters 1 through 5 in that book. And you see it, this is the home page. You see that link down here, the aftermath. That's going to take you to basically the output of this tablet PC and a video, which is the boilercast, if it works properly. It's not there yet, but it will be. So if you ever have to miss a class for some reason, you can always catch the lecture that way. I think it's better to be in class because then you can interact and be more disciplined about the whole thing. I've posted the first homework assignment on the home page there. There it is. It's from sections 1.1 and 1.2. And it starts out with definitions of sets and functions, etc. So it's fairly elementary. That's what I don't want to bore you to death with. But the second line there is about the mathematical induction, which is where I'll start talking about that next time. And there's more syllabus items there for you to, I'll click on that to show you what it looks like. The usual list of syllabus items. I cut it up into pieces so you can consult them. But especially the grading policy here is something you'll be interested in. We're going to have 2 midterm exams. The first one will be in class, usual kind of thing. And then the second one I usually like to make to be a take-home exam. It's kind of shorter and important that you do it, really perfectly and well. It won't be one of those take-home exams that works you to death. It's just a chance to shine on the subject, I hope. And the homework will be scaled to a total of 100 points. And the final exam will be 200 points, the usual business in a math class. Any questions about anything like that before we get rolling? Yeah, so let's see. My personal homepage is that thing I just wrote there, and the homepage for the course is continuing / capital MA341. Okay. I feel like that's the usual thing. No questions about anything? Yeah, I set inside back there.
Did we turn in our homework on grade 3?
That's what I'm figuring out in the next day or two. I'll let you know. At the moment, write it on paper and think about bringing it to class. The first homework is due next Wednesday. So, homework 1 on the home page. Due Wednesday, 117. And at the moment, think of it as paper in class, and I'm doing a discuss grade scope with my. What's your preferred method of doing homework? Grade scope or paper?
Grade scope.
Okay, that's my personal favorite too. So I wouldn't be surprised if we can do that because I believe my grader is familiar with it. The grader is an advanced graduate student. Let's see, I think you'll see it. Where did I put it here? Justin Enyart. And he's got an office in Map 1047. There's his email. And he'll be doing the grading on GradeScope, the homework grading. Of course, I grade the exams. Let's see, you had a question in front here.
Do our homework in the textbook?
Yeah, the homework is in the textbook. Maybe I'll augment it from time to time with something I create myself. I'll give you practice problems also that I tend to create myself. Yeah.
Which edition of the textbook do you want us to use? Because I looked at 3 and 4.
This is the 4th edition. Yeah, that's the problem with it. Probably the material is very much the same, but the problems will be out of order and different. So it's very important to get the 4th edition. Did I write that here? Oh, I didn't. I'll fix that. I'll write that on the... It's a typo. I'll fix it. 4th edition. And that's important. Other questions? Right. The book is the 4th edition. Well, I kind of wanted to do something more fun than the section 1.1 today because it's just, subsets and set theory and definition of functions and Cartesian product, the kind of stuff that would bore you to death if I just started blabbing it out. So I thought I'd tell you what sort of fired me up about real analysis, and it's the subject of Fourier series that got me really hooked on the business. And this history of Fourier series is really fascinating. The Bernoulli, I always thought they were the Bernoulli brothers, but it's the Bernoulli father and son. So Bernoulli versus Bernoulli. They actually had a competition to solve the vibrating string problem. And it was Johann Bernoulli, the son, who challenged his father, Jakob, to solve the vibrating string problem. Okay, so the vibrating string problem is I'll graph a moving string. Okay, so here the string is going to be blue. It's wiggling around. I'll stretch it from 0 to pi just to make it easier. And so this is an x-axis, and at x here, this little distance is u of xt. That would be the displacement of the string. And I like to think of this as a harpsichord string. So it's going to be plucked. Harpsichords are plucked. And of course, the harpsichord, the string is tied down at the endpoints. So it's got to be 0 here and 0 here. And when it goes below the x-axis, that u of xt is negative. Okay. Well, you can do Newton's law of motion for little pieces of string. And if the vibrations are small, you find out that the vibrating string, I'm going to do the harpsichord problem. If it was a piano, I'd be whacking it with a hammer, and that would give it initial velocity. I want to do the harpsichord problem because harpsichords have a quill feather that grabs the string, pulls it out, and lets go, so they get plucked. And so it has an initial shape, but no initial velocity. That's the deal, to make the problem easier. Okay, well, if you do physics, you'll see that this shape of the string, just by elementary F equals ma considerations, satisfies the famous partial differential equation called the wave equation. d2u dt squared equals a constant times d2u dx squared. Those are partial derivatives. Okay, so that's the differential equation that the thing satisfies. As an engineering student, I saw this stuff, and so I understood what I'm about to do from a distance, kind of. Let's see, so that we're going to know a couple of things. We're going to know that the endpoints, these are called boundary conditions. The thing is nailed down on the ends, so let's see, u at the left end point for all time is stuck at 0, and u at the right end point for all time is stuck at 0. And the initial condition is I pluck it. Okay, so that would be in time 0, and to make life easier, I'm going to pluck it in the middle. That'll make it sound like a rubber band. So it's got a kink right there. That's a kink is at pi over 2. So the initial condition is u, the shape, at time 0 is given. Some function. And I'll make it that pluck shape right there. And the fact that it's plucked means that the initial velocity is 0. Okay, so harpsichord is plucked. Which means the du dt, the x at time 0, is identically 0. If it was a piano, there'd be a velocity profile there. And that would make it a different, kind of a different problem, similar solution, but just more work. Okay, well, when Johann challenged dear old dad, by the way, his dad, Jakob, was his thesis advisor. And it seems like a bad idea to ask your dad to be your thesis advisor, because the two of them were very competitive and didn't get along too well. Funny, Johann didn't get along with his brother either, Daniel. Quite a family. Anyway, Jakob, being challenged and being the older thesis advisor, came up with a very clean, simple solution. Namely, u of xt is so simple that it's 1/2 f of x plus ct plus f of x of minus ct. So an absolute simple formula for the solution. And it's very easy to animate that and say, oh, yep, that works. That's it. So Jakob won, slam dunked the solution. Johann invented Fourier series to solve the problem. And so his solution was much more impactful because it started the whole subject of Fourier series. In fact, it started that subject before Fourier himself got involved. Fourier studied heat. Johann was studying the vibrating string problem. So Johann's solution he invented Fourier series basically to do it. And of course these are partial differential equations, and so that's a new subject back then. and needed new techniques, and there weren't any techniques at that point. There are lots of techniques now, but back then, Johann's big idea was to turn it into ordinary differential equations. So his big idea was try to find solutions of a special kind. That look like this: u of xt equal a function of x, so a function of one variable, times a function of time. This is called separation of variables, and sort of Johann was one of the inventors of this method for solving PDEs. People seen this before? When I was an engineering student, I saw it like 4 or 5 times before I actually started to understand it. You've seen it! You took the course on Fourier series from me. You can sleep if you want. Now let's see, to make the life easier for me, I'm going to let c be equal to 1. That was, c turns out to be the speed of propagation of the wave. So if this was electromagnetic radiation, c would be the speed of light. In the case of a string, it's the speed of a moving wave on the string. Okay, so I'm going to let c be 1 just to make life easier. And then we plug this into the PDE and see what we need to make it happen. So plug into PDE. Let's see, the PDE was dt, that's 2 partial derivatives with respect to t, equals du dx dx. When you differentiate with respect to t, that function, the derivatives would pile, this x of x would look like a constant, so it would stick out in front, and the derivatives would pile on the t function. And so x of x would sit there, and then this would be a t double prime of t. T is getting weird. What's going on? My eraser is not working. That's weird. Huh. That's weird, I'm sorry. T double prime. Okay, and when I pile the derivatives in x on, they would go onto the x side. So that would be x double prime t. And if you think about that, you sit there and see how am I going to make that happen. It's sort of irresistible to pull all the t functions to one side and all the x functions to the other. And stare at that for a while and realize I've got a function of t that needs to be equal to a function of x. How is that possible? Anybody besides you know? How can a function of t be equal to a function of x? Well, let's see. I could let x be pi over 2 and stick it in here. And then I would say, oh my gosh, the t function is a constant. And then I could let t be 10 seconds and stick t equal 10 in there and realize, aha, the x function is a constant too. And of course, they're the same constant because the t function had to be this one when I stuck in pi over 2. So I could let x equal pi over 2. See that the left-hand side is constant. And then I could let t be equal to 10 seconds, or 3. And we see that the right-hand side is the same constant. Okay, and so let's call that constant lambda. And this is where Johann thought he was making progress. those are two ODEs. So from one PDE, we got two ODEs. Okay, and let's see, x double prime minus lambda x equals 0. And how lucky, the t problem is the same. T double prime minus lambda t equals 0. Okay, but I haven't thought about the boundary conditions yet. So I got two ODEs. So now the boundary conditions. Let's say u of 0, t is supposed to be 0 because it's nailed down. That would be x of 0 times t of t. And we want that to be equal to 0. And we also need the other end, length pi string, to also be 0. So that'd be x of pi equal to 0. Well, one way to get that to happen would be, say, t of t should always be 0. That would be dumb. That would give me only the 0 solution. Okay. And we know that the string just sitting there is a solution. So that's kind of a dumb solution. The 0 solution. We don't want t of t to be identically 0. That would give me the 0 solution, which we know is a solution. Check. And so the other thing that has to happen if we're not going to do that is that x of 0 needs to be 0 and x of pi to be 0 needs to be 0. So funny, the boundary conditions for the string problem lead to boundary conditions for the ODE problem. Okay, this turns out to be a very famous kind of problem. This is a Sturm-Liouville problem. And they come up lots of places in science and engineering and math. Namely, x double prime minus lambda x equals 0 is the ODE, subject to not initial conditions, but boundary conditions. I figure out why my eraser is not working. Huh. Okay, it's a fun thing to solve, and I think I'll do it here today just to get rolling. Turns out there's cases to consider, and it's not always possible to make something that has those boundary conditions that's not identically 0. Of course, the identically 0 solution does that. Finding not identically 0 solutions is what we're trying to do here. So let's see, the case lambda equals, let's do some, there's going to be cases. The easiest one is lambda equals 0. Then it's just x double prime equals 0. And you integrate twice and you get that x of x is ax plus b. That's the graph of a line. And so if you ask yourself, how can I have a line? The line has to be 0 here and at pi. This is a line. It has to be 0 and at pi. Therefore, the only line that goes through those two spots is the flat identically 0 line. So we see that x of x is identically 0. So darn, we don't get anything from that one. So in this case, we only get the 0 solution. Okay, let's do the case lambda less than 0. No, I'm sorry, lambda positive. So let's write lambda equals something squared. That'd be positive. And then the ODE would be x double prime minus lambda minus k squared x. And the characteristic equation, everybody had an ODE class? Probably. The characteristic equation for that is r squared minus k squared equals 0. So r would be plus or minus k. And so the solution is x of x equals c1 e to the plus kx plus c2 e to the minus kx. And if you want that solution to be 0 at 0 and pi, well, let's see. Let's do the easy one. X of 0 would be c1 e to the 0 plus c2. And we want that to be 0. Which means we need c2 to be equal to minus c1. And so our x of x now we see is c1 e to the x e to the kx minus e to the minus kx, because c2 is minus c1. And if you graph e to, let's see. So I also need x of pi to be 0. And that would be e to the k pi minus e to the minus k pi. But when you graph the exponential function, e to the k pi is strictly bigger than 1. And e to the minus k pi is strictly less than 1. Because the exponential function looks like this. So e to the plus k pi is strictly bigger than 1, and e to something negative is strictly less than 1. And so there's no way that's going to be 0. So this thing right here is not 0. And so we must have that c1 is equal to 0. So once again, looks like bad news for Johann. It must have c1 equals 0, and of course c2 is minus c1, so it would be 0 too. So ouch, we get the 0 solution again. Looks like we're not going to get anything. But something finally happens in the next case of lambda negative. Let's see, then we'll write lambda is equal to minus k squared. Questions about anything so far? This is just for fun. It's not in the book. I just want to show you where Fourier series come from and why we need to think about analysis deeply to understand Fourier series. That's going to be the plan. Later in the semester, I'm going to show you that Fourier series do what we say they do. Let's see. So in this case, our ODE is x double prime plus instead of minus k squared x equals 0. And the characteristic equation is r squared plus k squared equals 0. And so we get roots, complex roots, r equals plus or minus ki. And that's a famous case in your ODE class. The general solution in that case is x of x equals c1 sine of x, kx plus c2 cosine kx. So let's see, x of 0 would be c1 times 0 plus c2 times cosine of 0, which is 1. And we want that to be 0. That's one of the boundary conditions. So So we have to have C2 equals 0. So there's no cosine term. Oh, it's looking bad again. And so that means that x of x is just C1 sine kx. Okay. And so now we also need x of pi to be equal to 0. That would be C1 sine k pi. Well, we don't want C1 to be 0 because that would give us the stupid 0 solution again. So we don't want C1 equals 0. Then we just get the 0 solution. So we better have sine k pi equals 0. And this is where Fourier series are going to come from. So we need sine k pi equals 0. And if you graph the sine function, you see that this is sine of x. Sine of x vanishes at pi, 2 pi, 3 pi, etc. Integer multiples of pi. So we need k pi to be equal to an integer multiple of pi. Pi, 2 pi, 3 pi, 4 pi, etc. Dot, 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 n pi. N is a natural number. And of course I can divide out the pi's there and see that I get need my k to be a positive integer. 1, 2, 3, etc. So those are the natural numbers. Okay. And so we got a whole bunch of lambdas that work, and so we get a bunch of solutions of lambdas. Lambda equals n squared minus n squared, where n is a natural number. And now we can start thinking about the t problem. So back to the t problem. The t problem was the same as the x problem. T double prime minus the lambda t equals 0. It's the same problem, and we get t of t equals, I'll put a1 sine nt plus, I'll make it a and b. Doggone it. That's weird. A sine nt plus b cosine nt. Well, let's see, when I stick in the n equals 0, the sine one is, the sine function would be 0. Sticking in. When I stick in t equals 0, the sine function would be 0. And the cosine function would be 1. So it's the second one that gives you the shape, and the first one gives you the speed of the wave. So I'm not going to dwell on this today. This gives you at t equals 0, this gives you the shape of this pluck, and this one would give you the velocity of the pluck, because it's 0. Velocity of the pluck, which is equal to 0. So it's reasonable to take a to be 0. I'm not going to think hard about that today. I just want to write down this solution. So here's what Johann got. Got u of xt, let's call it un of xt equals, let's see, the sine function was sine nx, and the function I'm going to get here is a cosine nt, the t of t function. So I got a bunch of solutions. And now you start worrying about the initial condition, which is the shape. And of course, you're sunk if you just think about one of them. So the initial condition. Well, you realize you take one, or you can even take 10 of them and add them up. You couldn't satisfy that initial condition because these functions wiggle. So the big idea that Johann had, and of course his father disapproved because he couldn't demonstrate that it worked. The big idea is to try an infinite sum of these basic solutions. Try u of xt equals a sum as n goes from 1 to infinity of all of these things. And not only that, but put coefficients in front. Sine nx cosine nt. That's the superposition principle. It's a linear PDE. The boundary conditions are homogeneous. If I add these things together, they all if they satisfy the PDE, their sum should satisfy the PDE. Finite sum certainly would. And also the boundary conditions are all zero, so the sum are going to have zero boundary conditions. So the superposition principle is valid. So we're going to try that. And so now the initial condition becomes u of x at time 0 is summation as n goes from 1 to infinity an sine nt. And this is the moment in history something important happened. This is a Fourier series. It's called the Fourier sine series. We want this to be equal to f of x, the Pluck shape. And of course, Johann must have sat around and thought about this for a very long time before he figured out what the coefficients have to be. Those functions, sine of nt, are orthogonal. So the key for Johann to get this to work is that sine of nt, it's nx's. The sine of nx functions are orthogonal on the interval from 0 to pi. And what that means is if you integrate two of them against each other, integrate from 0 to pi, sine nx, sine mx, dx. Let's see, if the n was equal to m, that couldn't be 0 because it's a square. So it's pi over 2 if n is equal to m. But amazingly, they're wiggling different speeds. They wiggle just right so that all the bumps cancel out. And so it's equal to 0 if n is unequal to m. And so this is an inner product of Johann started thinking of this like a vector inner product. So this would be the inner product of sine nx with sine mx. And it's just like orthogonal vectors. And that was the key. If you wanted to figure out how to expand a function in terms of orthogonal vectors, you would dot product that sum with one of them. Okay, so the key is I want f of x to be equal to a sum then goes from 1 to infinity of an sine nx. So Johann's brilliant idea was multiply both sides by sine mx. And I'll multiply this side by sine mx too. Okay, I multiplied both sides by sine mx, and now I'll integrate from 0 to pi, both sides. And here's something Johann did, because he had to. He distributed the integral through the sum. And of course, dear old dad didn't like that, because sometimes you can't do that, especially when you start thinking about deeper properties of convergence. There's conditions required to be able to do that, namely uniform convergence. Okay, and the miracle happens here. When you write these out, most of those integrals are 0, all except one. So this would be equal to 0 if n is unequal to m, and it's equal to pi over 2 if n equals m. And so what do we get in this infinite, what looks like going to be an infinite sum? It just spits out pi over 2 times a sub m. And so Johann realized that am has to be am has to be 2 over pi integral from 0 to pi f of x sine mx dx. And so Johann said, aha, I've solved the problem. My problem is that sum and the coefficients are this. If he had Maple back then, he could have shoved it in Jacob's face and said, yeah, look at it, works. These things really do converge to what we say they do. But of course, Jacob didn't buy it, and he had a better solution that was cleaner and easier to write, so he won the contest. Must have been kind of humiliating for Johann after all that work. But what a great moment in history, because it meant you could decompose any function in terms of wiggling sines and cosines. And that's the basis of, making electric signals with sines and cosines and alternating current and doing all kinds of mind-blowing things. It's also the key to understanding music in an interesting way, because this is the vibrating string problem that makes music. And it explains why the sound of a harpsichord is pleasing. I'll be serious and look at them. So the big question is, and this is one of the questions we want to answer in this course, which is why I'm doing this today, well, these things are easy to compute. So easy to compute for the shape we have, the puck shape, it's basically A1 equals 1 over 1 squared, A2 equals 0, A3 equals minus 1 over 3 squared, A4 equals 0, and A5 equals plus 1 over 5 squared, etc. And so we get the u of x at times 0 is 1 over 1 squared sine 1 times x minus 1 over 3 squared sine 3 times x plus 1 over 5 squared sine 5 times x, etc. And the big question is, does that really converge to what we want it to converge to? And so, those are all wiggling. And so it'd be mind-blowing that they actually sum up to something that is totally straight, TP-shaped thing. The answer turns out to be yes, and a lot of the stuff we're going to do was to, what Johann needed to convince dear old dad that this solution actually worked. And so these tools are important, and they were invented, a lot of them were invented, to study this problem and understand it. Turns out the convergence is very rapid and not terribly hard to see at nice smooth spots. But when things are not nice and smooth, then it gets much more subtle. And a lot of math was invented to study the not smooth spots. Okay, so I gave you this lecture today just to get you fired up about the subject in lieu of defining functions and boring you to death. So you need to read that carefully. Questions about Fourier series? It's a wonderful subject, and it's got me hooked on the more theoretical side of math. I went on to graduate school at MIT and studied pure math after my engineering undergrad days. But I really appreciated my engineering classes where this problem was studied to death. It's just we never dealt with the subtleties in the theory. And that's what I was starving for. And that's what I got out of a course like this that we'll have here. Anyway, I'll start working on learning your names and that kind of thing, looking at your pictures in Bytespace. The Bytespace is active now, but it's basically just links to the home page for you to click on. I did start a Piazza page. You're welcome to discuss the homework problems in Piazza, and I'll be monitoring them. And on the home page there, you see that my office hours are 2 to 3 on Tuesday and Thursday. You're welcome to come by anytime you want to talk about something. Last minute questions about anything? It's going to be fun. Okay. That feels like a place to stop. See you next time.
I just want to check to make sure I have the right version, because this does say edition, but can I just quickly check to make sure it's the same as yours?
So it's fourth edition.
These problems look right. Draw the diagrams to simplify the set theories and distributive properties.
I believe so. If it's a fourth edition, that's what they look like.
And then the last time I took this class, I took it last spring with Lampert.
Oh, yeah.
But the way he started it was we only started with the basic axioms. How much, am I allowed to assume in this class, which is what I need to state the definition for all that?
We're going to follow the book, so that's coming up real next, is this axioms. Can you turn this page? There it is. I got it. It's the same, doesn't it?
Yes, it is. Thank you. So, that's if it's assumed in the book, I can go ahead and assume on the homework.
Yeah.
Okay. Yeah, because that really messed with me when I was taking it last time, because I couldn't use the number 2 until week 4. So.
Oh, yeah, well, this time you have number 4, so that'll be...
All right. Thank you.
See ya.
Your complex course this afternoon is filled up.
Crap. People quite often draw.
Yeah, can I come later today even though I'm not complete?
I was surprised there were seats in here because they said this was full.